All right. So my plan was, I posted this last night, general study guide, and my plan was just to kind of go through here. But if there's anything you want to talk about, anything you want to review, or obviously any questions along the way, just say so. Otherwise, I'm just kind of going to go through this from start to end. It'll probably take us today and tomorrow. I don't know if we're going to need Friday for this also, but if not, we'll talk about some other stuff on Friday. Maybe we'll go over some C++ or something like that, just to round out things. But anyway, okay, so what sorts of things should you know for the final? So you should definitely know how to write code. Okay, this is a good idea for a CS major. And sometimes I'll ask you to write a whole program, sometimes I'll ask you to write one method, sometimes I'll ask you to make some changes to a set of code. If it's not clear what I'm asking for, just ask for clarification, right? Because if I want you to write a method and you start writing a whole program, you might be spending too much time. So writing some code or looking at code that's given to you and doing some kind of analysis on it, maybe making some changes to it or answering some questions about it, things like that. The idea that Java is an object-oriented language, okay, so that's a pretty fundamental notion. Also the idea that Java is interpreted, right? So C code, when you say GCC, it takes your C program, integer I, etc., and it turns it into basically ones and zeros that your CPU understands. Okay, that's compilation. Java takes your Java code, when you say Java C, and it turns it into an internal representation, which is called bytecode. And that bytecode, if you just dump that in the memory of your machine, it's not going to do anything. So there's a virtual machine called the JVM, the Java Virtual Machine. And when you say Java main, this program named Java, which is written in C by the way, opens up main.class and starts looking at the bytes in there, and it interprets what they mean, and it does whatever your program is asking it to do. So the C code is going to run faster, right, because it's running directly on the hardware. But if I compile my C code here and then I take it to a different machine like an ARM processor or an old Z80 processor, right, it's not going to run. My class files, after I've said Java C and I've got my .class files, I can take those to any machine that has the Java command, and it should run those without recompiling, because it's the same bytecode, right, because Java is a virtual machine that's interpreting those bytes the same way. So that makes Java code fairly portable, extremely portable, right? And you can develop code for a Raspberry Pi, and you can run it on an x86, and so on and so forth. You should be pretty comfortable with the idea of object-oriented things in general. Okay, so this idea of taking data and taking code that manipulates the data and bundling those together into a single thing. Okay, that thing is called an object or a class. And so it's this idea of encapsulation, right? So we have a bunch of vectors, which means we have x, y, and z coordinates, and we'd like to be able to take their length with the length function. We'd like to be able to normalize them with the normalize function, or add them together, or do a dot product, or things like that. Data and code, and this code goes with this kind of data and vice versa. So you bundle those all together and you make a class called vector. And if you want a vector, you can just say vector v, and now v is a vector, and v has all of those functions built in, v.length, v1 dot product, v2, and so on, right? So it encapsulates all that into a single object. So that's one of the key ideas of object-oriented design. Another is information hiding. Since the object comes with the code built in for manipulating the data, the user doesn't necessarily need access to that code, to the internals of that code or to all the pieces of data, right? Inside the class is code that can access any of the fields. If your code is going to do something with those fields and the outside world doesn't need to touch those, you can hide them. Okay, and this goes along with the idea of abstract data types. So here's what the vector object looks like to the outside world. It's got x, y, z coordinates, you can find the length, you can do a dot product, you can normalize, right? And that's it. And how is that implemented? Doesn't matter, right? Maybe it's implemented with integers, maybe it's implemented with doubles, maybe it's implemented with fairy dust. Makes no difference, right? The interface to the user is uniform. And so this encourages code reuse and so on and so forth. All right, definitely know basic Java syntax, okay? I'm not going to nickel and dime you to death on things like semicolons and curly brackets and should it be parentheses exception E or curly bracket exception E, right? I'll ding you a little bit the first time I see these, but in general, the syntax that I'm going to notice is the stuff that we've been doing repeatedly, right? We've written try-catch blocks numerous times, especially PA5, right? So you should have a really good idea how a try-catch block is laid out. How a class is defined: class, name of the class, curly bracket, stuff, close curly bracket. Public static void main, parentheses, string, bracket, bracket, variable name, close paren, curly bracket. You've typed that or seen that, you know, a gazillion times. So basic syntax: if-then statements, for loops, while loops, declaring variables, assigning values to them, stuff like that. You've been doing this for your programming assignments and so on, so just kind of review that. Put the tricky things down on your note sheet if you like. Classes and methods. So everything is a class, right? And the way you define a class is, you know, keyword class and the name of the class, curly bracket and curly bracket. And then mostly inside here you either declare variables, okay, which are part of the class, or you write methods, functions, right? And that's really what makes up the class. So once you've defined a class, you can declare an object to be of that type. So you've got class, my class, etc. Say I want an object of type my class. It's just my class, you know, whatever your variable is called. Okay, that's a declaration. It says variable is an object of type my class. But if I try to do something with variable, it's going to give me a null pointer exception. Okay, this is saying integer I without saying I equals some particular value. So before you can actually use this variable, you have to construct an object of type my class. So var equals new, and then you call the constructor, which has the same name as a class and takes 0 or more arguments. And that's kind of doing what you would do with malloc in C. That's actually allocating memory, but it's also potentially running some code to do some initialization, and now var actually refers to a full-blown object of type my class. So we also call this an instance of the class. So var is an instance of my class, and sometimes this is called instantiation or construction. To access pieces of an object, we just use a period. Okay, there's no need for an arrow notation because we don't have pointers. Even though this thing is kind of a pointer to the object, if we have, you know, integer j and character c, and we have some function which does something, right? I can say variable.c, and that refers to this character. I can say variable.function and pass an integer, and it calls this function with x equal to 12. Okay, so we use the dot that we use to pick off pieces of a structure in C. All right, and then there's signatures. So in C, the name of a function makes it uniquely identified. Right, if you have a function named blah, right, anytime you try to call a function named blah, that's the function that's being called. You can only have one function with that name. In Java, the name of the function is only part of what identifies it. What's the other thing that identifies a function? So the type of arguments that it takes. right? And the return, for some reason, actually isn't part of it. But the type of arguments that you pass to it, along with the name, that defines a function uniquely. So that's called the signature of a function. So you have a function that takes an integer, you have a function that takes two integers, you have a function that takes a character. Those are three different functions, even if they all have the same name. And in your code, when you call this function, the JVM will look and see what you're passing to it. Oh, you're passing a character, okay, I'm going to use that function. You're passing two integers, I'm going to use this function. Okay, so that's the signature of a method. And it just extends the idea of how do you identify a particular function. And so this pops up a lot in constructors, and we've done this with rectangles endless times, right? We had a rectangle constructor that takes a height and a width. We had another version that only took one integer, which made a square, and we might have had one version that took no arguments and it just made a 1-by-1 rectangle, right? Three different signatures, three different constructors. All right, so statics. So last time through on statics, so here's a class. It's got an integer x. It's got a function named fun. It's got a static integer s, and it's got a static function called cool, and it's probably got some other stuff. Alright, so if I make an object of type haha, haha h equals new haha. To dereference, right, to access pieces of this, I can say, for example, h.x equals 5, or I can say I want to execute h.fun. Okay, and these things are called instance fields, instance methods. Okay, they're the way that we normally run things or access things associated with an object. But these things that are called static, s for example, I don't need to say h.s. The way that I should access s is by the name of the class .s. So that's a static variable. And I could run this method called cool by saying haha name of the class dot cool. And that's a static method. These are also called class variables or class methods. So instance variable, instant method, that's just using an instance of the object, right? H is an instance of the object to say particular haha, right? It's using that instance to access these elements. Static variables or class variables are using the actual name of the class to access them. And we do that, you know, if for some reason it makes sense to allow somebody to run the cool method without having an object of type haha. So math is sort of the classic example. If you do math dot sign, right? We don't need a math object. We just want to run the code in this method. So this is a static method in the class math, and so we can say math dot sign, and it runs the sign algorithm. All right, various data structures that we've used. So arrays, certainly, right? That's sort of our first data structure. Lists, linked lists, trees, things like that. So I'm not going to expect you to know, the internals of the linked list class or the Hashmap class or things like that. If I asked you a question involving the linked list class, I would probably give you some documentation like, here's get that we can use to get an element, or index of to find where an element is, and so on. So I'm not expecting you to memorize that, but I'd like you to know that there is a linked list class, there is a Hashmap class, and so on. Okay. Yeah.
If you ask us a linked list, like program question, would we use the linked list class, or would that be something you would?
I would probably say don't use it.
Okay.
If I ask you to make a linked list and I don't explicitly say don't use the linked list class, ask me about it, because it's probably an oversight.
Okay.
Otherwise, there'd be nothing to write.
So we haven't done any hashing for this quarter. Should we kind of assume we're not going to have any hash map questions, or should we try to?
Well, we went over hash maps. Right, we made the 5-line version of the word index program using hash maps, where we used phrases as the key, and then we stored the index count as the value associated with it. But it was a one lecture kind of thing. So, you know, take a look at the documentation. But again, if I was going to ask you to do anything with it, I would give you some documentation on methods and such. Definitely expect to see some recursion, okay, in some way, shape, or form, because you can't talk data structures without recursion. Trees, you know, you did decision trees for your 20 questions game. Lists, you've made lists of lists, right, for your word index. So you're most likely to see questions that involve writing code or analyzing code related to linked lists or trees or things like that, possibly using recursion. So generics. So we touched on this with linked lists and hash maps and some other things, right? A linked list of strings, a linked list of integers, a linked list of doubles, a linked list of rectangles. The code's always the same. The only thing that changes is when you have your search method, the argument should be a string or an integer or a double or a rectangle. But the actual code for moving through the list and comparing two things and so on, it's always the same. So there's this concept of a generic, which says I'm going to write a piece of code that works with more than one type of data. Right? So linked lists are an example of this. The linked list class itself works with a generic type of object called E in this case. Okay, so there's a type parameter E, it's the type of elements held in this list. And when you use a linked list, you just need to tell it what you want that E to be. So if you want a linked list of strings, you do something like this. You do linked list and then in angle brackets the type of object. And I might call this list equals new. And the rest of this looks exactly the same as usual. And linked list you can construct without any arguments. So the only thing that's happened here is instead of just using the class name, we're using the class name followed by angle brackets and the type of objects in the structure. And that's what this linked list bracket E is telling you. And so a hash map takes two types of data, a key and a value, right? So the key is what you use to look up and the value is the thing associated with the key. And those don't have to be the same type of object. So when you construct a hash map, you pass it two type parameters, which are called K and E here, and you put them inside the angle bracket with commas, and now you've got a hash map that takes rectangles for keys and decision trees as values associated with each rectangle. Right? And it works perfectly fine, even though that would be a goofy thing to do. So that's the idea of a generic. We did not talk about how to make generics. I think I might do that on Friday if we have time left over, just so you've seen it, because it's fairly useful to actually define a class that works on a generic type. It's really easy. You basically just put a parameter in your class declaration, and you use that parameter instead of int or string or whatever. But it's still cool to actually see. Another concept related to these is iterators, and we touched on iterators, and they pop up in linked lists. So linked lists, arrays, it's easy to look at all your data, right? If you have an array of 10 things, it's set an index to 0, go all the way up to 9, and just grab each of your things. That's easy. If you have a linked list, maybe there's a way to look at the first element, the second element, the third element. Okay, but depending on where that firewall is that lets you not see below that level, there may not be a sort of natural way to pull out all the elements in your linked list. A hash map, there's really no inherent ordering to that. It's a set of keys and a set of data. Unless you know what the set of keys is, there's no way to access all the data. And there's no such thing as the first key, the second key, the third key. So these methods, these classes have what's called an iterator, right? And an iterator basically works like a scanner. You get an iterator, and then you can say, well, iterator.has next, and that'll be true if there's another item in your data set, and you can say iterator.next, and it'll return the next item. And so it's a way to sort of pull things out of your data structure one at a time and know when you've seen everything exactly once. And they don't expect you to know the code for constructing that, just the concept of it. But you know, if you have to use it, you just go through the documentation or you find an example, and it's just getting it to give you an iterator and then using that to construct something you can iterate on. Alright, so strings are one of the classes I do want you to know details of. So you should definitely know the length method. You should know the equals method for seeing if two strings are the same. Compare to for lexicographical ordering, right, sorting. Character at for getting the nth character of a string. So you can't use brackets because it's not an array. So you can say string.character at 2 gives you character 2, which is the third character. And then the toString method. So strings are peculiar in that if you have, say, a rectangle, and you've constructed it hopefully, if you say string s equals plus, and you try to concatenate, so plus is a concatenation operation. It says take two strings and put them together. There's a string. This is not a string, right? But I'm asking it to concatenate it to this as if it were a string. So it's actually going to take R and it's going to call a method toString, which should return a string. Now I got a string and a string. Those can get concatenated. So anytime I take a string and I try to do a plus with an object, the system will automatically call that object's toString method. So we use this as a way to present some sort of meaningful representation of an object by writing our own version of toString. So if this was a rectangle, we might say, you know, a rectangle with length 10 and height 5 or something, and so it would concatenate that string. And there's always a toString method by default, and it prints out the name of the class and an @ sign and a hex number, but we can make our own. Or, you know, we could explicitly concatenate r.toString if we want, right? Or we could just say s equals r.toString or whatever. It's just another method. The only quirky thing is that if we just do this concatenation, right, it automatically calls toString for us. And we've been using that from the beginning, so I think people are clear on that. Double equal versus equals, right? So double equal we almost never want to use with objects, because double equal is saying, is this object the same as that object? So I can have two rectangles exactly the same height, exactly the same width. If they're not the same rectangle, double equal will return false. Okay, I could make an equals method for rectangles that says if the heights match and the widths match, return true. Okay, but that's not what double equal does. So strings have an equals method which compare character by character. So if I have two strings and they have the same characters, dot equals will return true. If I say equal equal, it'll probably return false, unless they happen to be the actual same string, you know, the same object in memory. All right, class extensions. So we started to do this when we were doing GUIs. We had panels, JPanels, that we wanted to make changes to, and so we extended them. We've done this with threads also. We make things that extend threads so that we can use some of the features available in the thread class. So class, new class, extends old class. And then you do all your usual stuff. Okay, so you're defining a class called new class, right? This is all what you're used to. By adding this keyword extends and naming another class, basically all the stuff that's available inside old class is now available in new class. So it says I want to start with all of this stuff, but I'm going to add some more stuff to it. And if I write, for example, my own version of a method that's already available in old class, it overwrites that method. Right? So whatever I put in here will take precedence. So old class has a toString. I write a version of toString. If I just say toString, it's going to use the one that I wrote. But if I wanted to get to the toString method in the old class, I can use the keyword super. So I can say super dot some method name or super dot some field name, and if I happen to have made my own version of it, doesn't matter, it'll still take it from the original class. If I haven't made my own version of it, super doesn't really do anything, right? Because the version of that method in here is the same as the one in old class. But it lets you overwrite methods and fields but still get to the originals. And that's useful sometimes. Maybe I want to augment the toString method of the rectangle class. Maybe right now it says, you know, height by width, and I want to change it to say a rectangle of height by width with area blah, right? So I could call the original toString method to get that middle part or whatever. All right, arrays. So arrays are slightly different in Java. So I can say integer bracket bracket x says x is going to be an array. This is like saying integer star x. It declares x to be an array of integers, but it doesn't give it a value. And if I try to use x bracket 0 or x bracket 2, I'm going to get a compile error saying it may not have been initialized. So to actually make this thing an array, we have to say x equals new int, and you have to tell it how many integers you want. So an array of 10 integers. There you go. Oh. Oh, that's okay. Alright, so there it's going to complain x might not have been initialized. I don't know why it says might not, because it obviously knows it hasn't been. If it was guessing, it would probably let us just go ahead and compile. So I think it's being polite, like you might want to check that. Alright, so I can do that. And that works fine now. And you can do this in one step, obviously. So just like int star x equals, you know, address of whatever. So that works.
Maybe it's because they didn't want your error message to check and see if you have setters or getters. For example, if you initialize there, but your next line is some other code, or anything else is called in that code, sent to your array, somewhere else in a different file.
Okay.
You would initialize it.
Right.
And so they're saying it might not have been initialized because it can't detect whether or not you have an external program interacting with it.
That's probably true. Okay, I'll buy that. So you can still go out of bounds, right? There's an array of 10 integers. If I try to access x20, compiler doesn't know, but when you run, you get the array index out of bounds exception, right? That's an advantage over C, because in C, if I say integer star x and then I try to use x bracket 1,000,000, it'll happily try to access that location in memory. And if it exists, it'll give it to me whether or not I meant it to be a part of the array. So there's the start of some buffer overrun exploits that we can take advantage of, perhaps. So Java is supposed to have that locked down. All right, so primitives, right? Integers, doubles, floats, booleans, these lowercase things, this works fine. For objects, this doesn't actually work. So if we say rectangle, assuming rectangle is a class, rectangle x equals new rectangle bracket 10. All right, now I'm allowed to do something like, say, x bracket 2. That exists, that's well defined. But if I were to try to call, say, the area method of that rectangle, I'm going to get a null pointer exception.
Because there's nothing in that spot.
Because there's nothing in that. It's an array of 10 references to rectangles. I didn't say pointers. 10 references to rectangles, but they're not actually referring to any particular rectangle. So before I could do this, I could say something like x bracket 2 equals new rectangle, and construct your rectangle however. And now I can say, show me the area of that. So with arrays of objects, you kind of end up using new twice, right? Once to actually make the array, and then again to construct each object inside the array. That's the only slightly quirky thing about it. But I shouldn't call it quirky. It makes sense somewhere. So that's initializing the array versus the objects in the array. The other thing is the length field. So there's an array of 10 integers. I haven't given them any values, but since x is an array, it has this field called length that'll give you the length of the array. So there it tells me x dot length is 10. And this is not a method, right? If I try to call the length method like that, it's not even going to compile because there is no method named length for an array of integers. But as a field, that's always defined for arrays. And if x is just an integer, right, it'll complain about that. So it's just for arrays. All right. Good enough for now. Oh, I skipped ahead to class extensions, didn't I? That's okay. Did I skip anything down to here? Okay. So scanners, print writer, system.in, flushing, buffer.io, new file. So let's start from that tomorrow. We'll go through try-catch block. And then we'll start talking about GUIs. And this pretty much takes us up to where we were for the midterm. Okay, so I think I don't know if we included try-catch on the midterm, but somewhere around there was where we left off. And then when we got to GUIs and event handlers, threads, sockets, and networking, that's all post-midterm. So we'll start from there tomorrow.